Welcome. Today's lesson is entitled Graphs of Polynomial Functions, Day 2. This lesson is just a continuation of the previous lesson where we analyzed the graphs of polynomial functions and looked at some of the specific characteristics. We looked at, if you remember, what's called end behavior, and we'll go ahead and review that characteristic here today. We also looked at the zeros and their multiplicities and what that meant graphically, and we'll of course review that as well today. And we'll go ahead and add the third characteristic, what is called turning points. So actually I'm just kind of looking at my board right here, and if you get a chance, write on your paper, next to turning points, can you write max/min? So the minimums or maximums on the graph, that's what we'll go ahead and look at here. So that's what a turning point is, either a local max or a local min. And let's go ahead and see if we can come up with a nice pattern here. It looks like I have 5 polynomial functions just on your paper. Let's go ahead and put the degrees in place. They're not in any particular order, and I kind of did that on purpose. But it looks like I have a nice degree 5 or a quintic function on that top one. Looks like I have a cubic, so degree 3 right there. Quadratic, so degree 2. Quartic, degree 4. And then, of course, a linear function. We didn't really do a whole lot with linear functions, but it is certainly a polynomial. So all of these are under the polynomial umbrella, and that's what we'll take a look at here today. Now what's kind of fascinating is the relationship between the degree and the potential number of turning points. So I created these 5 functions right here so they would perfectly fit our pattern, but we do want to be very clear on the conclusion that we draw from this. So it would be great if you could go ahead and grab your calculator. I'll do the same, I don't mind. And let's go ahead and graph these. And what I'm looking for is just the number of local maxes or mins. So let's go ahead and do x to the 5th minus 6x cubed plus 8x and plus 1. All right, I hit, let's go zoom in number 6 there, that standard window, and a nice quintic polynomial function on the coordinate plane. Just to remember, let's talk end behavior a little bit here. End behavior, fall, rise. So we would call that fall, rise, end behavior. Looks like you have a bunch of zeros here, 1, 2, 3, 4, 5 zeros, all singles kind of going through. But regardless, let's go for this one. Turning points. Here's a turning point right here, kind of changes from increasing to decreasing. So this is a max right here, a min right here, a max and a min. So I'm hoping that you do see that there are 4 turning points there. All right, so I'm going to go ahead and put exactly that piece, 4 turning points for that quintic. Let's go ahead and continue. Now that you kind of understand what we're looking for, let's go get that cubic there. So x to the 3rd, how about a 3x squared minus 6x and minus 8. I'll hit graph again, and maybe not the optimal window for this, but you can see there's a turning point right there, a local max right up there, and how does a local min right down there sound to you? So I'm seeing 2 turning points for this cubic. So let's get that into the mix. Quadratic, we've done a lot of work with quadratics already, and we should know how many turning points a quadratic has. I'll just very, very quickly put that in, but you know, you should understand the graph of the quadratic and as a result how many turning points. And you know, the turning point of course is the vertex, and in this case it's a min right down there. So it looks like it would be 1. Great. Let's go get this quartic. Doing nicely here. I'll keep putting these in. X to the 4th minus 2x squared. And how about the plus 1? I'll hit graph again. And not the best window there, just use your imagination, but are you seeing a min, a max, and a min? Hopefully everyone's all right with that. So 1, 2, 3 turning points in this one. And that would be the case right there. And then I'll tell you what, I'm not even going to graph this. If it's a line, everybody, and picture this line with a y-intercept of -4 and a slope of 2, how many turning points does a line have? 0. And so take a look, obviously, at the connection between those 2 columns here and see if you can come up with a pattern. And so based on the degree, here is the potential for the number of turning points. And so let's conclude it. Let's be done with this piece. A polynomial function of degree n can have at most, now guys, I bolded it, I underlined it, circle it too, please. At most, I'm hoping you see it's n minus 1 turning points. So that's what you saw here, degree 5, the 4 turning points. Degree 3, 2 turning points. Now, here's where we have to be careful. Does it mean that every degree 5 polynomial has 4 turning points? No. What it means is a degree 5 polynomial can have at most 4 turning points. It will never ever have more than 4. Okay? So a great graphical characteristic that goes with this family of functions, and now we can put that in place with all the others, the n behavior and the multiplicities of zeros, and we'll just try some, good basic examples here. Given graphs, can you come up with a model? Given a model, can you come up with a graph? That type of thing. Let's see if we can put some of that together. All right, well, let's go get them. Example 1. Determine whether or not the graph can represent a quadratic, cubic, quartic, or quintic function. So here's what we're going to do. Let's do the 4 graphs first. So as a matter of fact, let's go ahead and give me 4 coordinate planes, kind of side by side there if you get an opportunity. 1, 2, 3, 4. And what I'm going to do, is draw 4 graphs of polynomial functions. So that, remember from what we talked about yesterday, they're going to be continuous, they're going to be nice, smooth, rounded corners, all that good stuff. And just very generic in nature, no tick marks or anything like that. If you could copy these, that would be the ideal. So maybe something like this would do. Okay. For the next one, I've got something like this, give or take. Okay, next one right here. How about that? And then one more over here. There we go. Good. So as you can see, they're all continuous, and they all sort of model what we would consider to be the graph of a polynomial function. Now what I would like for us to do is kind of get specific with this. Now, first of all, I took linear out of the equation here because, you see none of these are lines. So a linear equation, a linear function, even though it fits under the umbrella of being a polynomial, I kind of took that out of the mix. So we'll just focus on the ones that we do the most work with, which would be the quadratic, cubic, quartic, and quintic. Theoretically, I could keep going with this. I could do a degree 6, degree 7, degree 8, etc., no end in sight. But I narrowed it down at least a little bit. And so I guess I would ask you this. This graph right here, is it possible to create a quadratic function to make a graph like this? If the answer is yes, then write the word quadratic here. If the answer is no, then don't. Same with cubic. Is it possible to create a cubic function that would form a graph that looks like that? If yes, write cubic below. If no, then don't. And that's what you're going to do for each of these, quadratic, cubic, quartic, and quintic, for each of these 4 graphs. Try it. Would love for you to pause the video and see what's going on there. If you're not sure, if you're still unable to kind of decipher what this problem is asking, no big deal. Then just kind of wait for my explanation. But I would love for you to pause and see if you can understand the nature of end behavior, turning points. Zeros don't come into play too much here, but really the 2 out of those 3. All right, well, I'm going to give it a try. So I'm going to run down my list. Can this be quadratic? Well, remember, a quadratic is a degree 2, and a quadratic has only 1 turning point. This one has, as you can see, 1, 2, 3 turning points. So it cannot be quadratic. Too many turning points for a quadratic. Cubic. Well, a cubic, if you remember correctly, is degree 3. A cubic has at most 2 turning points. This one has 3, so this one has too many turning points. Also, let's go ahead and refresh from yesterday's lesson. Isn't the end behavior all wrong for a cubic? So remember, cubic, being an odd degree, has opposite end behavior, either fall-rise or rise-fall. Can't be fall-fall. So end behavior is wrong for a cubic. Quartic, Yeah, it could be quartic. Could have 3 turning points. And is the end behavior okay for a quartic? Absolutely. So quartic is even, end behavior is going to be the same, fall, fall. Does that make sense? And then quintic, could it be quintic? Well, I guess the turning points we could consider it being okay, because quintic has at most 4 turning points. But here's the end behavior. What do we know about quintics? End behavior is opposites. Here the end behavior is the same, so it cannot be quintic. Good. All right, now let's go a little quicker if we can on B, C, and D. Quadratic? Nah, end behavior is wrong on quadratic. Cubic? Yeah, I have cubic on my list here. End behavior is right for cubic. Rise, fall. And remember, cubic has at most 2 turning points. This one doesn't have any, actually. It's just decreasing all the way through. But it's all right. Quartic? Nope, end behavior is wrong for quartic. Quintic? Yes, indeed. Can be quintic. So quintic, end behavior is right. They're opposite. And remember, quintic, the turning points has at most 4. This one doesn't have any. It's fine. Good. Letter C, quadratic? Oh, absolutely. We've seen graphs like that before. Nice parabola, quadratic would be perfect. Cubic? No, no. End behavior is wrong for cubic. Can't have rise, rise for cubic. Quartic? Yeah. Actually, we can do quartic on this. So end behavior is the same, rise, rise. That's good for a quartic. A quartic has at most 3 turning points. This one has 1 turning point. That's fine. So quartic is good. Quintic? No, it can't be quintic. End behavior is wrong for a quintic. Last one. Quadratic? No way. There's so many reasons it's not right. Cubic? End behavior is good for the cubic, but look how many turning points. 1, 2, 3, 4. Too many turning points for a cubic. Quartic? No. End behavior is wrong, of course, and the number of turning points is wrong. So not quartic. The only one that I think works here is quintic. End behavior is fall, rise. That's good for a quintic. And 1, 2, 3, 4. That would be the case also for a quintic, potentially. All right, nicely done. So I'm hoping that just solidifies a few of the things we've talked about, just in broad terms. Time to get a little more specific with these functions. So let's go ahead and do example 2. Write a polynomial function for each graph, and we'll do it in factored form. And so let's go ahead and sketch one out here just as best as possible. Here's what I'm going to ask you to do. Give me a fairly elongated coordinate plane, kind of horizontally there, so stretch that out a little bit horizontally. No tick marks on the y, but give me some tick marks on the x, if you would. And let's see if we can kind of sketch this out together as best as possible. And I guess here's what I'm going to ask you to do. Can you throw a point at -5 for me on the x? Could you throw a point at -3 on the x-axis? Can you throw one at 0 on the x-axis? Can you throw one at 2? And can you throw one at 6? It's 2, 4, and something like that. Okay, so those are going to be our zeros. Now, guys, our end behavior, I think I'm going to do it this way. Let's go sort of a rise that way. And then past this one, let's do a fall this way if possible. And then here's how I'm going to play it out, everyone. I'm going to try to draw this in a nice continuous fashion, of course. Smooth, rounded corners, all that good stuff. Touching and crossing through all these zeros. So if you're ready, let's sketch with me. So should go through here, touching here and coming back. Sorry, let me just make sure I have this right. There we go. Crossing here, and then touching here and coming back and meeting up with the end behavior. So not perfect by any means. And one thing with this particular problem is the location of these maxes and mins are going to be kind of irrelevant for us. So ignore those. Just know that there is some max right up here. There is some max right here, et cetera, et cetera. But what I want us to do is be able to write a function that would essentially match that graph. So let's give it a try. If you want to do f of x equals, you're more than welcome to. I'm just going to do it y in terms of x. And then let's kind of reboot from yesterday a little bit and think about the zeros of this function. You could see those numbers on the x-axis there. And remember, one of the conclusions we drew yesterday was basically that zeros come from factors. And that's how we're going to write this in factored form. So basically, when I see a 0 of -5, that's this one right here, we all know that that comes from a factor of x plus 5. Now do me a favor, leave a little room out in front, but I need us to go ahead and write a factor of x plus 5. So that would produce a 0 for this particular function. Okay, good. Now I also see a 0 at -3. -3 comes from a factor of x plus 3. And so we know that x plus 3 has to be a particular factor of this function. Okay, good. Now, here's the good one right here. I have a 0 right at 0. What is the factor that produces a 0 of 0? Well, I'm hoping you would agree that it's just x, right? Now, you could put the x right here if you want. A lot of students like to put the x out in front, by the way. I'm going to put it right back here. It's fine. Again, it doesn't matter. The order is irrelevant. But I would argue at this stage I've done something slightly incorrect. And the question is what? And I'll give you a hint. I crossed at -5, had my x plus 5. I crossed at -3, had my x plus 3. But now I'm touching at 0. What do we know about the multiplicity of our factors if it's a touch at that particular 0? And what we know is a touch comes from an even multiplicity. So squared is obviously the easiest thing to do on that, and so that's why I'm going to put a squared right there. Does that make sense? Okay, good. Let's keep going. It looks like I have a 0 at +2. What factor produces a 0 of +2? Well, x minus 2 would produce it. Okay, good. And last one here, it looks like I have a 0 at 6. And so what factor produces that 6? X minus 6. Again, let's be careful on this piece. If you look at it, it is touching at the 6. Touching and going right back down. And so what do I know about the multiplicity? It must be even. And so a squared on that. All right. Now, a couple things that go with this. There's one piece missing that I'd like to account for right out in front, and that would be the leading coefficient. I have all my factors, and we'll talk about those factors in a little more detail in just a second, but I would love to go ahead and just explore that leading coefficient right here. So what's the deal with the end behavior here? Look at the end behavior. The way I have it, it looks like it's rise, fall, end behavior. Does everyone see that? Rise, fall, end behavior. Well, what do I know about rise, fall, end behavior? Well, number one, it comes from an odd degree polynomial, right? So let's see, this is in factored form right here. If I was to multiply this out, which of course we're not going to, it would be some polynomial of degree, I don't know. Well, rather than multiplying it out, let's just count up the factors. So you ready? 1, 2, 3, 4, 5, 6, 7. So this is, at this stage, a degree 7 polynomial, which is odd. And what else do I know? It's a degree 7 polynomial. And if it's rise, fall, and behavior, what do we know about the leading coefficient? It must be negative. So we don't have to be too detailed there. You could put in any negative number. That's what I'll write. Any negative leading coefficient would work here. That's what makes the graph go from potentially fall-rise to rise-fall. So in this case, I just threw a little negative out, -1 essentially. but whatever. Does not matter. It looks good. All right. By the way, I guess we came up with the degree 7 here. Let's count turning points. I'm just curious. 1, 2, 3, 4, 5, 6. Okay. So for a degree 7 polynomial, it can have at most 6 turning points. And this one, the way we did it, it does. Great. All right, now letter B is going to be a touch harder. So a little asterisk by that one. Watch this one. So give me a coordinate plane if you would, and a tick mark right there, and 2 tick marks right here. And then here's what the graph is going to look like. And actually, before I forget, 1 tick mark up there. And so here's how it's going to play out. Going to do this, going right on through that point. Let's do a touch at the 1 and a cross at the 2. Arrows right there. Okay, very nice. So I have a couple zeros. Well, actually, I have 3 zeros. 1, 2, 3. And I also have another point that I'd like for this graph to go through. So a little more specific than the last one. In this case, I didn't have a scale at all for letter A. Now I just have a slight scale in that I want it to go through this particular point right here. Okay, good. Well, I think we're going to have to do a little work on this before actually putting something in the answer blank. But let's see what we have going on here. So let's start it out, everyone. If you would, give me a little y equals. Leave some room out in front. And then let's kind of figure out what's going on here just based on what we did in the previous problem. I'm hoping now we can run with this a little bit in terms of we have a cross at -1, which means I probably have a factor, a single factor of x plus 1 right there. Okay, good. I have a touch at +1, which again, we can interpret a variety of ways, but maybe something like that right there, x minus 1 squared. I have a cross at +2. How does an x minus 2 sound to you? Is everyone okay with that piece? Now, rather than just putting any old leading coefficient out in front here, what I want to do is get the specific leading coefficient to not only match the graph here with these zeros, but also to make sure it goes through this particular point. So what I'm going to do is actually call that leading coefficient A, because I don't know what it is just yet. I have an idea of what type of number it's going to be, but I don't know what it is. So let's see if we can go ahead and find it. Any ideas on how we might find it? So I would like that leading coefficient right there, which means I'm probably going to have to do something about all these x's and the y. And as a matter of fact, if you look at this carefully, I gave you one. I gave you an x, and I gave you a y. And if those correspond together on the graph, then I can put them in the equation because it makes it true. And that's what we're going to do. We're going to utilize that point. So the 1 is the y value. Again, the leading coefficient is what we're trying to find. The 1 is the y when the 0 is the x. And so now I solve for the leading coefficient. I hope that makes sense. And again, you can see the differentiation between letters A and B here for example 2. Okay, very good. Well, let's go ahead and solve this. And by the way, what type of number do you think we're going to get when we solve for A? Look at the end behavior, guys. Fall, fall. So it looks like I have come up with a quartic at this point. 1, 2, 3, 4. 4 factors, so a degree 4. That makes sense. And fall, fall. So I know this has to be some type of negative number. I don't know what. Let's go ahead and find it. So let's see. I've got 0 plus 1, which is just 1. I have 0 minus 1, which is -1. But then I'm going to square -1. That actually becomes 1. And then 0 minus 2 is just -2. So all of this is just multiplication, right? So I've got 1 equals A times 1 times 1 times -2. Are you okay with multiplying that together and just saying that's -2? And do you want to divide that -2 on over? And when we divide that -2 on over, hey, look at that. Very nice. I end up getting a is equal to negative 1/2. I had mentioned that I knew a would be negative just because of the end behavior. And yeah, there it is. It matches exactly what I thought would occur. So it looks like we're ready. I'm going to go ahead and put this in place. Again, factored form is nice. You don't have to multiply anything out here. So in this case, rather than any negative leading coefficient, I want the proper one. So it's negative 1/2. Now the factor of x plus 1 is in there. The factor of x minus 1 is in there, squared for the touch. And x minus 2 is also in there. And there you go. I won't waste our time by graphing this on the calculator, but if we were to graph that, it should match this graph pretty well. Tough to kind of tell in here if that's the max or whatever, but irrelevant. It goes through the point, and that's what I was looking for. Okay, good ones. Let's go take care of example 3, just switching it a little reverse. I give you the function, you give me a sketch. At this level, of course, we'll ignore the location of the turning points, just acknowledging that there's got to be something in there somewhere. All right, so a coordinate plane, if you would. Kind of elongate it horizontally if you get a chance. Just we'll see how this works. Throw some tick marks on the x, none on the y, that's fine. And let's talk about just some of the basics here. This is polynomial. It's in factored form, which is great. And let's see what we've got going on. First and foremost, in terms of the degree, let's count the variable factors. So here's the leading coefficient, negative 4. And the variable factors producing the 0. So I have 1, 2, 3, 4, 5. So this is a degree 5 polynomial. And a negative out in front. So you can maybe envision the end behavior. I'm hoping you can. Well, let's get some zeros in place and then see if we can sketch. So what 0 comes from a factor of x? Well, just 0. Put it in right there if you would. What 0 comes from a factor of x plus 5? Negative 5. 1, 2, 3, 4, 5 right there. And what 0 comes from a factor of 2x minus 3? Well, if you were to set that to 0, you don't have to do this on your paper. If you set that to 0, and that's how it works as factors, it looks like you end up getting 3/2. So 1.5 would do, and that's good. Okay. All right. Now, I gave you a moment there to think about end behavior. What is the end behavior of a quintic, degree 5, and a negative leading coefficient? And I'm getting this as a rise-fall situation. Rise-fall for the end behavior. So I have my 3 zeros here, and what's kind of interesting, to the left of this leftmost 0, the end behavior takes effect, basically, because it's not going to turn and come back. So it's going to rise. And so to the right of this 0, we know we have the other part of the end behavior, which I think we already determined was fall, because it's not going to turn back and go towards the x-axis again. Okay, so let's go ahead and sketch this out here. The question is, as I approach the 0, is it a touch or is it a cross? And as I approach that negative 5, look over here, everyone. It's x plus 5 squared, so you know it's going to be a touch at the negative 5. So let's go ahead and get that. It touches there and comes on back. And now there's got to be a max somewhere in here because it has to come on down to this 0. Touch or cross there. Probably a cross because it's a single factor right there. And then let's go ahead and get the next one. Somewhere between here and here is a minimum. So it's below the x-axis, but it's coming back up. Touch or cross. And it touches and goes on down. All right. Now it's an interesting looking graph, but you know, in essence, the characteristics are in place. In order to get the positions of these maxes and mins that you see, we do need calculus for that. And so at this stage, we just kind of avoid that piece. There's a max somewhere here and a min somewhere here. Wonderful. We'd love for you to try to do letter B, kind of set up the same thing. See if you can put it all together. So I'm going to go ahead and get some tick marks going as you guys are thinking about this as well. 2, 4, 6, and 8 looks for me. There we go. And let's see if we can pull this off. So first order of business is, let's do some zeros. I've got -2 right in here. -7. See, 2, 4, 6, and 7 right there. +4 and +8. Okay, good. Let's look at this one and talk about end behavior. So look at all the variable factors, count them up. That would tell us our degree. So I've got 1, 2, so 2 factors, 3, 4, 5, 6, 7, 8. So a degree 8 polynomial. So if I made you multiply this out, which would be crazy, you would get a big x to the 8th out in front with a 3 actually as the leading coefficient, so it would be a 3x to the 8th. And because that leading coefficient is positive, that means we're talking rise, rise. Even polynomial degree and positive leading coefficient. So rise, so rising to the left of that and rising to the right of that. Wonderful. And now it's just a matter of doing the continuity piece all the way through and touch versus cross. And so let's just do it. Cross at the -7. Let's see, next one I'm going to hit is the -2. And coming on back, it looks like a touch at the -2. Next one, I'm coming back down. I've got to go get that 4. How about a touch at the 4? And then comes back down. Again, these minimums kind of down here. And then we've got a triple, which means it's going to cross. Triples act a little differently than singles. It kind of levels off a little bit before shooting on through. Be something like that. So it is still a cross. It does act a little different. I don't care how you graph that. Obviously, as long as you have that right there, that'd be great. One connection, and then I'll move on to the next piece. Just in terms of single versus triple, I'll keep it simple. What if I made you graph something like this right here? Hey, we all know we would all graph y = x like this, right? Just a nice line. Really shoots straight on through that 0 right there, right? But y = x cubed is a little different. It doesn't shoot right on through. It kind of acts like this. And that's what happens for any 0, single versus triple. Kind of cool. They're both crosses, but you could see this one acts a little differently than this one right here. Okay, good. I'll erase that piece. Just wanted to give a quick explanation on that, but no worries. All right, let's go get the next, which is letter C. So this one is in standard form. So I have x cubed plus x squared minus 4x minus 4, cubic. Leading coefficient is +1, so we could already talk end behavior on that. But I think I'm going to need some zeros on this, so let's go ahead and get factored form. Remember grouping, guys? Let's group it. So if I group this, I get x squared, x plus 1. Take out the -4, so -4, x plus 1. There we go. Looking good. Do you see that these two terms have an x plus 1 as a factor? So let's factor out that x plus 1. And when I factor out the x plus 1 from here, I get x squared. Here's my minus. When I factor out the x plus 1 from here, I have a 4. Nice. Good factored form right here. I could probably go a little further on this. If you'll do the same with me, that would be great. But I do see a difference of 2 squares there, so I'm thinking x plus 2 and x minus 2. Super. Now it's in factored form, and now we're ready. This one's not too bad. I think we've got some things taken care of here. Throw some tick marks in, and let's see it. So 3 factors, 3 zeros that come from them. How about one at -1? How about one at -2? And how about one at +2? Did you ever decipher that end behavior on this one? I'm getting an end behavior. Since it's odd and positive, end behavior, I believe, is going to be fall, rise. All from yesterday's lesson. Make sure you have that squared away. But it looks like now they're all crosses, so something like this. And that would be that graph right there. A great looking cubic. All of it comes together beautifully. That's what I like about this. even though we're talking about distinct characteristic traits here, they all fit within this nice coherent system. So the fall rise meets the multiplicities, which meets the turning points. Cubic can have at most 2 turning points, and there they are. Cool. All right, so again, just putting the characteristics together. I like that piece. Let's go do the one application and round this out a little. So example 4. You've potentially seen this problem before in a couple different contexts. This is just a good place to do this problem. So a rectangular piece of sheet metal, 16 inches by 12 inches, has squares cut from each corner, and the resulting flaps are folded up to form an open-top box. Let X be the amount cut from each corner. Alrighty, so let's do this like we've done it before. I have a 16 by 12. And what we're going to do is cut out squares from the corner. They have to be identical squares. So 1, 2, 3, 4. There are theoretically an infinite number of ways to cut those squares. So what we're going to do is put our variable on them, x by x, to show that that can change. And if you kind of remember correctly what this would look like, and I can never do this justice with drawing, but I'm going to do my best anyway. When I go ahead and take those squares out, I get a figure that might look something like this. There we go, not bad, could be better, could be worse. And the idea behind this particular problem, of course, is you would fold up the resulting flaps. So this folds up, this folds up, this folds up, think 3-dimensionally here, and it would form an open top box. And that box, of course, has a length, width, and height, which is how we get the volume. So let's go ahead and put volume equals length times width times height. And potentially, again, you've seen this before, where we're able to express all 3 dimensions in terms of x. So let's go through our diagram one time. If you've never seen this before, then I'll go through it nice and slow for you. If you've seen it, you could probably fast forward a touch and write those in and get moving with the next piece. So the length of the box, if you can visualize it, would probably just be from here to here, because these flaps have folded up. And we started at 16, and I took out x from this corner, x from that corner, and so as a result, I had 16, and I took away 2 x's. The width of the box is from here to here. Same deal, I started with 12, but then I took out x from here and x from there, and so that would be 12 minus 2x. And last but not least would be the height of the box. Again, think 3-dimensional as that flap folds up. And if you remember, since I think we have seen this before, the height of that box is the flap right here. It is that. It is x. And so there is your height. Length times width times height. So let's write this as a function. This looks great. Good practice constructing functions here. Volume in terms of x. And there it is in all its glory. If you were to multiply this out, you would get a nice standard form cubic function, which happens to look something like this. I'll go ahead and just highlight it, where there's going to be a nice little maximum in there, and that's exactly what I'm going to try to find. So it says, what is the max volume of the box, and what are the dimensions of the box that produce the maximum? Let's bring the calculator up one time here. Good opportunity for us to do that. And let's type it in. So I go 16 minus 2x, 12 minus the 2x, and then the x. I'm going to hit window, and just to expedite this along, let's see if I have a decent window for us. I'm going to go 0. 10 is fine. I think that's more than adequate. And then I'm going to go 0 here. I'm going to do a few hundred and see what happens. Let's see if that was decent. Yeah, not bad. Actually came up with a good window. Okay, so there's our cubic. If we were to extrapolate, of course, look at the end behavior because it's cubic. Fall, rise, and behavior. So the leading coefficient is definitely positive. Cubic, it does have the 2 turning points, one max and a min down here. That one's irrelevant for our purposes here. But as you can see, nice maximum right up there. So out of the infinite number of ways to make this box, there is an optimal way to maximize that volume based on some particular x. Let's find it. Ooh, and there it is. So remember what's going on here? There's the max. This is the x value that produces the best volume. This is the best volume for this box. So I'm going to write a couple things down right here just for a moment. It looks like the volume is 194.07, and this would be cubic inches. And then I think I saw this, because we're going to have to do this piece. I think I saw the x value that produces it is about 2.26. Well, again, I don't think I need inches on that, so let's take that off. But a 2.26 in terms of the x value. Is everyone okay with that piece? Now, could you give me the length and width and height if I have the x? Yeah, here we go. 16 minus 2 times Rx, 12 minus 2 times Rx, and then the x. Well, I'm just going to give you these values so we can wrap this up here. I'm just looking at my time and overdoing it just a touch. So if I put 2.26 back in here, I end up getting a length of about 11.48 inches. If I do the same right here, I end up getting a width of about 7.48 inches. And then the height, of course, was that x value, which is about 2.26 inches. Alrighty, a good problem, it's a good place for it, talking about turning points and different characteristics on those functions. I think they all come together quite nicely. All right, well, I'll wrap it up here. Please let me know if you have any questions along the way. And of course, thank you so much for listening.